first, a little bit about me. I am a final year PhD student at the University of Southampton in the UK. My supervisor is Professor Stephen Terrio, and I'm looking for jobs starting in the coming academic year, starting in 2023. So my research is at the moment principally in classical homotopy theory, and so given a manifold, one may wonder whether it is decomposable as a connected sum of simple manifolds. And my PhD thesis studies this highly geometric problem from a new homotopy theoretic perspective. And amongst other things, it contains two papers which are viewable online via these archive links. And in this presentation, what I'm going to do is I'm going to talk about the results from this first paper, and then talk about the results from the second one, just very briefly, and then I'll conclude with some current research projects and also some speculative ideas for where things could be taken. Okay, so the first paper is about a homotopy theoretic analog to this theorem of CTC walls from 1966. So let M be a six-dimensional manifold with some of the usual adjectives. Then there's this diffeomorphism of M as a connected sum of two guys, M1 and M2, and M1 is a connected sum of finite many copies of pairs of product of three spheres, and this all that we know about this mysterious M2 is that its middle homology group is finite. Okay, and one may ask whether there is a higher dimensional analog to this question. I want to try and provide a homotopy theoretic answer to this question. Okay. So let's start with a bit of language. So given a homotopy covibration like this, a map F is called inert if the base loop map on the map H has a right homotopy. So you can think of this maybe as the base loops on C retracts off loop B via this map loop H. Okay, and so this is the sort of one of the main homotopy theoretic gadgets that we're going to sort of try and play with. So given two n-dimensional CW complexes X and Y, and let's suppose they just have a single top-dimensional n cell, then X bar and Y bar are their n-1 skeleton, and there is a pair of homotopy covibrations like this. So we attach the top set of X by F and the top set of Y by G. Okay, and F plus G we construct as this composite. So I take the usual co-multiplication on Sn and then do F on the left-hand side, G on the other, and I go into this wedge of the two skeleton. And the homotopy cofiber of this map is, I call their connected sum. And when X and Y are, say, manifolds that have the homotopy type of a CW complex, and these manifolds are simply connected, then we are in such a situation. And then this connect sum agrees with the usual connect sum that we're used to. So we have these three homotopy cofibrations, and just a very quick little lemma. I want to think about what happens when F is inert. So when F has this inertness, let's just say the map X bar to X, when I loop it, it has a right homotopy inverse. Then I could construct one for F plus G as well. So F is inert, and so is F plus G, and there's a homotopy equivalence. The loops on the connected sum split in this nice way, where the symbol here is this left half smash. And this is sort of the main machine that if we want to develop a homotopy theoretic analog to the Theorem of Wall, then we throw it into here, and we play with these kinds of ideas. And that's precisely what I do in the paper. But I don't do it for manifolds. I do it for Poincare duality complexes. Now this is just a finite simply connected CW complex where its homology, cohomology satisfies Poincare duality for all coefficient rings. And a smooth, simple connected closed manifold is going to fit. Is going to be a Poincare duality complex. So this is a legitimate thing to do. And the analog is this. So let M be an n-2 connected two n-dimensional Poincare duality complex, and n here is greater than 3. And this condition here, this technical condition, avoids cases where you have maps of Holton invariant 1. And I say that the rank of the middle homology group of M is this D, and I would demand that to be greater than 1. And then I'm saying there exists a homotopy equivalence like so. So after I loop M, it splits as loops on a connected sum of these three manifolds. So M1 is an n-1 connected to a dimensional Poincare duality complex with the rank of the Hn of M1 is D. M2 is this connected sum of finite many copies of Sn-1 and Sn+1. So this here we're actually doing better than Wall. We have an extra summand that we can get off with this homotopy theoretic version, and then M3 is analogous to Wall's M2. So it's this mysterious guy who hn of M3 is finite, and that's all that we need. So this is a homotopy theoretic analog to Wall's theorem. So there is a trade-off. We sacrifice some of we have to loop first, but we do get this nice homotopy theoretic analog. Okay, so that's the first paper. The second paper deals with this question of Jeffrey and Selick. It has a slightly different flavor to the previous thing. So they start actually with a fiber bundle of manifolds, but I want to speak about this in homotopy theoretic language. So we begin with a homotopy fibration of finite CW complexes, and this X has dimension n and Y has dimension m. And we're going to take another M complex, call it Z, and form the connected sum as we did in one of the previous slides. And this leads to a pullback diagram like this. Okay, so the bottom row is the fibration that we started with, and the connect sum as a canonical pinch map to one side. So I pitch down to Y, and then I pull back. I label this map from P to X pi, and this map from the fiber into Pi, I call that alpha. Okay. The question is, to what extent does P quote unquote look like a connected sum? Okay, and Jeffrey and Selick discuss this in their paper. They're looking for results for different things involving quantum line bundles. We don't take it that way. I want to sort of think about an answer to this question. To what extent is P like a connected sum? And so that's the diagram again. The proposition is that if this map P after I loop has a right homotopy inverse, then so does loop pi. And if the map from F to P is null homotopic and the attaching map of the top set of X is inert, then after I loop P, it has the homotopy type of the loops on a connected sum, where W is this guy that I construct. I have this half smash F and Z bar, the skeleton of Z, and I glue on an M cell. Okay, so this is a very niche situation, but we can understand it a bit better if we can do a bit better. I mean, if we go to rational homotopy theory. So cell attachment like this is rationally inert. The map is F is rationally inert if loop H induces a surjection on rational homology, and in particular after we rationalize spaces and maps, loop H therefore has a right homotopy inverse rationally, and this definition inspires the definition of inertness that we had before. So he's playing with this kind of inertness, these inertness games integrally when we're moving back rationally now. So we're sort of making this double turn, having been inspired rationally before. But there is this beautiful theorem of Halperin and Lemaire, which says that if after I glue on a cell, I actually have a Poincare duality complex, and the rational cohomology of this guy in the middle A, if that rational cohomology is generated by more than one element, then the attaching map F is rationally inert. And they get this by playing around with the Sullivan algebra, and that gives them the conditions what they need to do this. Okay, so moving to rational homotopy theory now, and considering our setup before, our diagram where all the spaces are Poincare duality complexes, analogous to this original formulation of Jeffrey and Selick that I mentioned, we have this result. So given spaces and maps as our setup, where all spaces are Poincare duality complexes, if the map from F to P, this alpha is rationally null, and we have this simple condition on the rational cohomology on X bar and Y bar, then rationally there is a homotopy equivalence as loop P looks like the loops on a connector somewhere. W is the same as before. Okay, so we have this nice rational homotopy theoretic answer to this question: to what extent does P look like connected sum? And again, we have to loop, and his problem sort of involves connected sums. So that's the result. So that's all I really want to talk about at my own research. So current projects, there's this conjecture by Vigue-Poirier, which is about the growth of the rational homology of the free loop space of a space X. And there could be some connections from my work to this. And this is sort of an ongoing project. That more work needs to be done here, but this is something that my supervisor and I are working on. And more speculatively, there could be connections to chromatic homotopy theory or homological stability problems in the style of Oscar Randall Williams and his co-authors. And we have also maybe a connection to Moore's conjecture, which is this profound, strong result that deals with exponents, which I don't really have time to talk about. But yeah, so that's what I wanted to talk about today. So if you watched this video and made it through to the end, thank you for your time. Here's my email address. I'll be at session 1 of the networking event. and my personal webpage is there. So thank you.